Yeah, yeah.
Hello, good evening, everybody. Am I audible? Is my screen visible? Presentation visible?
Yeah.
Yes, yes.
Okay, thank you for the confirmation. So, once again, a warm good evening and welcome to today's tutorial session on urban utilities planning, water supply, sanitation, and drainage. I think most of you have already been there in the previous session. But just to introduce, so I'm Jeslu. I will be handling the tutorial session for all the week. So we have met before, so I'm not going into more details. So today we will look into some of the numericals and some of the questions pertaining to week three. I'm assuming that most of you have gone through the lectures already and have started attempting the assignments. So we'll look into some previous years' questions so that we can solve our assignments easily. So these were the topics which we covered this week. We looked at rainfall, runoff, and groundwater. What are the different properties of groundwater? So we saw what is groundwater yield, permeability, how does porosity influence groundwater. We learned about different characteristics. How does water aquifers, how do water flow through the aquifers, what are the characteristics of these aquifers on and what is the specific yield or uh, how can we predict how much of water we will get from an aquifer or from a well. So that's from the groundwater perspective. Then we learned about what are the different sources of groundwater. How do we intake open wells, confined aquifers, tube wells, uh, yeah, infiltration galleries. So all those different ground intake measures, infiltration, those comes in surface water intakes. So for surface water and groundwater, we looked into different intake measures. What are the structures that we construct for that? And then we also looked into groundwater yield. How do we design our wells, or how do we calculate how much of water can be pumped from a particular well, and where do we locate our wells so that so that we get adequate amount of water, and how deep should we dig the well? So all these simple properties we learned in this week's week 3. So we will look into some numericals for this. So today we'll first look into a few numericals because these calculations are important, and then we'll look into some theory questions also. So before we begin, I guess most of you already know this. We'll go question by question. After each question, you can ask your doubts pertaining to that question. By the end of this session, we'll have a discussion about any other question that you want to ask, or something which we discussed also. But one recommendation is, if we can restrict our discussion to week 3, it would be good, because that's what we will be discussing. Week 4, if you have any doubts, you can hold on, and we'll discuss that in the next week, or week 1 or 2 also. If you have any doubts, you can always discuss that also. So yeah, so let's get started. If you have a calculator, you can, scientific calculator, if you have, you can keep it with you, because for today's calculation we would be needing those. And as always, we will work together, so I urge all of you to work with me so that you can tell me the answer. So let's make it more interactive. So let's get started. Question 1. A real estate project on a 15-hectare site contains 8 high-rise apartment buildings, each with ground coverage of 2% of the site area, and houses a residential population of 18,000. 40% of site area is for landscape gardens and parks. The rest of the area is for roads and open parking. The site experiences rainfall of 1,580 millimeter annually. Assume the coefficient of runoff for landscape area and roads and paved area to be 0.15 and 0.06 respectively. The average surface runoff from the site after a heavy rainfall of 150 millimeter in 2 hours is. So we have been asked to find the surface runoff. So the question is asking us to find the surface runoff, and we have a lot of information given over here. Maybe we don't need all this information, so let's break the question down and figure out what is given and what we need to find. So we know that surface runoff is what we need to find, and we also know that, so we have both, we have annual rainfall information given, and the rainfall from the site of for 2 hours there's a rainfall. This information is also given, so we will take any one information in order to calculate, because we we don't need both the information. So what is given is, you have a site and the site area is given. What is the area of the site? Anybody? What's the area of the site which is given in the question?
15 hectares.
Yeah, 15 hectares. So I'm leaving it as hectares itself, because in calculation we can leave it that way. So this is what is given. There's 15 hectares, and there are eight high-rise buildings. So 8 high-rise buildings, and each of these building has a ground coverage of 2%, which means each of the building covers 2%. So the total coverage would be 2% into 8, because there are 8 buildings. So the site coverage will be 2% into 8 into the total area that we will do. And what else do we have? We have 40, sorry, one sec. Yeah. So we have 40% of the site area is for landscape gardens and parks. So in this you have around 40% of the site area you have for landscape, and then the remaining, which is not given, the rest of the area is for roads and pavement. Fine. So why we are doing the separation of landscape area, build up area, and roads and pavement is that we know that there's something called coefficient of runoff. That is, or if water falls on a paved area, the amount of runoff which will be there from the paved area would be different from the amount of runoff which would be there from a landscaped area, even when same amount of rainfall is falling on these two areas, because of the material property or because of the soil characteristics of that area. And based on this, we have a factor called coefficient of runoff, which gives us an idea of how much water is being absorbed into the groundwater and how much will be going as surface runoff. So that is why we are separating this out so that we can calculate what will be the runoff separately from each of these areas. So we have three areas which are given over here. So while calculating surface runoff, which all will you calculate? So you have you have the building which comes in your build up area, build up, build up area because of the building. And then you have, so that's your one, then you have your landscape area, and then you have roads and pavements. So will you calculate runoff for all the three separately and then add them up? Is that, or does anybody feel that we will eliminate any of these? Like we don't need 1 plus 2 plus 3. We only need 1 plus 2, or we only need 2 plus 3. Any observations?
all all are required.
All are required. Okay. Okay. Anybody, any difference of opinion? Okay. Okay. So let's go into, let's calculate each one, and at that time, we'll see. So, okay, I think before we calculate, we'll clear that up. So, one thing that we are is, so what happens is if you have a roof, so if you have a build, you have an apartment, for that build up area where the apartment is there, or where the ground is built with this particular apartment, or if it's a house or any other build up area which has a roof, usually we have certain laws by which we need to take the water which is there in the roof directly using pipes on as groundwater. So the roof water which is there, it comes through the pipes, and it's mostly directly, the pipe is given to an underground channel and it goes as groundwater directly. It is not put on the surface, or there's no, it's usually the pipe does not end like this and the water falls on the ground and that has to come down. Like it's not there. It directly goes as groundwater. And also, since this is build up area, you don't, in that particular region, there's no percolation, or there's no water which is going down, or there's no runoff happening on that particular region because there's a building over there. It's only the roof. So whatever water is coming through the roof is directly taken onto the as groundwater. So we will not take the runoff from the built area or where the apartments are located. That area we will subtract from the surface area, because what we are essentially finding is a surface runoff. And there is no surface runoff happening from these area where the buildings are erected. So this one, or this build up space, we will not consider the runoff from these regions, but we will consider the runoff from 2 and 3, which is the landscape area and road paved area. So let's get started with that. So just to write things again, so we have site area, which is our 15 hectares. I'm leaving it as 15 itself. Now we have a building coverage. So as discussed, the building coverage area will not come in your surface runoff calculation, but we need it in order to find how much area is dedicated for roads and pavements. And because roads and pavements, it's not directly given in the question. If you look, it's given that assume the rest of the area is for roads and pavements, roads and open parking. So to get the rest of the area, we need to subtract the area taken by landscape area. So to get 3, we'll have to subtract the area taken by landscape area, which is 2, and the area by the building, which is the building coverage. So this 1 and 2, we'll have to subtract from the overall area in order to get 3. So that's why we will calculate this. So the building coverage, so it said that there are 8 high-rise buildings, so 8 buildings, and each covers 2% to 2 by 100 into the building, the site area which is given, which is 15 hectares. So how much does this work out to? I'm waiting for your answer. You can put it in the chat box or you can speak it out. It's a very simple calculation. It should not take time.
2.4.
2.4. Very good. 2.4. Now, how much is the landscape area? Let's find how much is the landscape area. So landscape area, how much percentage is it given for landscape? 40 percentage of the site area is for landscape. So 40 by 100 into 15, how much does that work out to?
Six.
Correct, yeah, 6. So this is for landscape. Now for roads, we as we were said, we discussed for roads we have the remaining area, which means 15 minus 2.4 plus 6. How much does this work out to? Okay, simple calculation. So I'm just going ahead. I see only Galif answering. I guess others can also answer. I mean, these are simple calculations, but when we do it together, it would be more interactive and interesting. And most of the doubts will get cleared when you do it together. Or else when you're solving it for the assignment, at that time, some doubts may arise, especially when it comes to changing of units and all that. So when you do it together, it's more easy. So I would request all of you to like do it together with me so that it becomes easier. Right. So now we have the pop. Yeah. So now we are going to find out to calculate the surface runoff. So let me just write down the other information also which is given. So population information also is given. Like we have 1,800. Let's see whether we need it or not. But I'm just writing down the information. We also have the annual rainfall information. Annual rainfall, which is 1580 mm in the question. Just confirming. Yeah, annual rainfall 1580 mm, correct. So residential pop, yeah, okay. And we also have the coefficient of runoffs given. So for landscape area, the coefficient of runoff is 0.15, and for roads and paved area, it is 0.65. So let's write that. So coefficient of runoff for landscape area, it is 0.15, and for paved area it is 0.65, right? So yes, and we also have one more information given, which is the rainfall which is there at that particular time. So there's a rainfall of, how much is it? 150 mm for 2 hours. So we have a rainfall of 150 mm for 2 hours. So these are all the information that is given. Now, what is the, oh, I'm running out of space. Okay, sorry. Let me just add a page so that, give me 1 minute. Yes. So what's the formula which we will use in order to find surface runoff? We have learned, so there is an empirical formula which we have been using. So can somebody give me the formula? What is the formula which we will use? Okay, so we find the surface runoff by using this formula, CIA by 360. So where C is the coefficient of runoff and I is the intensity of rainfall, which is there, and A is the area where it's falling. So this we have discussed in detail in the lecture, in one of the lectures. The derivation of this is also given on how we get this 360 factor and what are the units that we are using. So this is the formula that we are using. So for this, we need only the intensity of rainfall and the area. So other information which is given like population, annual rainfall, all that information we do not need in order to solve this particular question. So intensity of rainfall, we wrote in the other one, that is 150 mm in 2 hours. So this one, intensity of rainfall in hours, is what we will be using. That is why we have a conversion factor 360. So for this formula, the intensity duration is given in hours. So if the intensity of rainfall for 2 hours is 150, for 1 hour, what will be the intensity? 75. 150 divided by 2. So for 1 hour, we have got 75. So for each, now for landscape area and paved area, we will separately find the surface runoff. So first one, Q for landscape area. So I'm just putting it as L. So that is C, which we wrote down over here, which is our 0.15. So it'll be 0.15. Yeah. So 0.15 into I, what is the intensity of rainfall, which is this one, 75, into what is the area for landscape area, which we found over here? It was 6 hectares. So into 6 divided by 360. How much does this work out to? 'Yes, I'm waiting for the answer.
0.1875.
1875. Yeah, okay. So 1875 why am I getting a different answer? Yeah, 0.1875. Correct. 0.1875. You're right. Absolutely right. And thank you, Khalif, for answering all the questions. Please continue to do so. I again urge others also to answer, or at least put the answer in the chat box if you don't want to speak it out. It would be really great. So yes, so that's a landscape area. Now for our roads and open parking. Again, C is, let's go back, it's 0.65. So 0.65 into 75 into what's the area? 6.66 into 6.66 divided by 360. How much does that work out to?
0.893. 894.
0.894. Very good. Yeah, 0.894. So the total runoff will now be the sum of this both. So that's 0.19. Okay, I'm just so yeah. So why I'm doing this is in the question it's written that, let's go back to the question, correct it to two decimal places. So after you sum it up, you need to correct it to two decimal places. So yeah, you can sum it up and then correct it to two decimal places, or yeah. So what is the final answer that you're getting? Add this both up.
1.08. Because the
1.08.
fuel is,
Is it, sorry, you were saying something?
yeah, right, that's right.
Yeah,
M cube per
yeah, what's the unit? Meter cube per second, because it's the
second.
volume, yeah, the runoff that you're having. So meter cube per second is what you're taking. So you might be wondering that we used hours over here, that there is 1 hour is what we are inputting. For 1 hour, what is the intensity? In millimeters is what we are inputting for intensity, but our unit over here is meter cube per second. But it's correct. The reason why we have a 360 over here is because this automatically takes care of this millimeters. It converts the millimeter into meter and the hour into second. So that 1000 by 3600 which we get, that is, sorry, 3600 by 1000 which we, so based on that is where we are getting this factor 360. So the unit is always meter cube per second. So this is the answer. Is that there in any of our options? It's there as option A in the question. So this is the correct answer. Any doubts? And anybody? I am unable to answer because I'm traveling. Oh, that's totally fine. Just pay attention, and if you can do some calculations while you're traveling, you can put it up in the chat box also, Parthasarthi. It's okay. It's good. It's very good of you to inform that in the chat box. So at least some interaction. So this is also good. Yes. So anybody? Any doubts? No doubt. So very good. So let's proceed on to the next question. So this is a series of questions. So three questions based on this information. So the question goes, consider the following diagram and the observations made on a 30 centimeter diameter tube well. The rate of pumping is given. It's given as 1500 liters per minute. The drawdown in the test well 30 meter away is 1.5 meters, and drawdown in another test well 60 meters away is 0.6 meters, and the depth of the water in the well before pumping is given to be 40 meters. So why does this happen? Like, what are we essentially talking over here? So there is a so there is a there is a well, and it has a water level. So let's say this is the water level in the well. Now, after water is drawn out from this well, the water level in the well is reducing. Yes, you're taking some water out, so the water level is reducing. So when this water level reduces, there is a bend, there is a bend in the groundwater level. So if this was the initial groundwater level, there is a bend. So because when water is drawn from this well, water from the adjacent regions will also rush into the well and will come inside. It's not that it's only from this particular region, because in the end, in the bottom, there is no demarcation. So water from the surrounding regions will also come. So because of this, there is a bend in the water table. So this bend influences the region around it. So there is a radius for which there is an overall region for which this bend is F. So instance, you have a bend. Yeah, so that is what is shown over here. So because water is drawn from this well, the water table, or the level of the water table in a nearby region is also reducing. There is no drawing of water from this well, but then it is reducing. This is reducing. So we do not know what this is. These are called test wells, which are built in order to find what is the water level at a particular distance from our actual well. So using these test well, we will find out what is the radius for which there is an influence. So what is the radius for which the water level is bending, or at which point the water table starts to bend. Now, why this is important is because when we are constructing a well, if two wells are constructed very close to each other, then because of the bends in water table, or because of excessive drawing of water from one well, there will be no water in the other well, or the water level in the adjacent well will also get influenced because of that. So which means that if you're constructing a well over here, then probably initially you had digged this much because the water table is over here, but by the influence of this, you will if the depth of the well is only this much, after drawing water from this well will go completely dry. There will be no water in this well. So which means you will have to dig the well a bit more deeper, so that even after accounting for the bends in the water table, you will still have some amount of water. So because of this, the cone of influence, or the cone by which the water table is bending, is important. So this is the theory part of it. So now we will look into some questions on calculating the radius of influence, or what is the discharge from the well, all that. So the first question asks about the radius of the circle of influence in meters, which is this radius, or the overall cone from where the bend is happening. So that we do not know. In order to find that is why we are constructing all these test wells, and using some relationship with these test wells, we will be finding that out. So we are using one formula over here which we discussed. It's called the Thiems formula. So Thiems formula gives a relationship between the water level which is there in the well, and the radius, or the distance from the actual well to the cone where the water level is there. And based on this, we will be able to find out the quantity of water which is there, and we can equate that. So let's come on to that. So I'll just write the Thiems. I'll just write Thiems formula over here. Q is equal to Km into h square minus h square divided by log 10 R by R. This is the formula, where Km is a transmission coefficient of the aquifer. So why this is important is because for every aquifer, the transmission coefficient will be different based on the properties of the aquifer, or the rate of flow of water will be different. So we're using a coefficient of transmission coefficient for each aquifer. Now H is the depth of the well. By depth we mean, let's go back. So this is the actual depth of the well. So this is H, so this is the initial depth of the well. So that's we are talking about, and in the question it's given to be 40 meters. So this is H, And then we have another h, the small h, which is the current depth or the depth of the test well or where the water level is. For instance, here of the test well. So this is the test well. So the current water level is here. So this is h, the small h. So we have two test wells. So this becomes h1 and this becomes h2, this height. Now in the question, this height is given. That is how much to how much level the water drops down. So that is what is written over here. The drawdown in the test well 30 meters away is 1.5 meters. By drawdown, we're talking about the amount by which the water level is reduced because of pumping from the actual well. So that is 1.5 meters. So in order to find this h, we will have to, so h1 will be equal to 40 minus 1.5, because this is the information which is given over here and this is h1 or h what we need. So that is this h, which is the depth of test well. Depth of test well. Now we have r, which is our radius of influence, which is what we are interested to find in the first question. Just to repeat, radius of influence is the radius or the point from which the water table starts bending. So why it's all in radius again? Because these are all concentric circles. Like for instance, you have a well over here. Now because of this well, at some point in space, at some point at an equidistant region, at a point equidistant from this well, the water table starts to bend. So this radius r is what we are interested to find. And how we will find this is by constructing small test wells at certain distances and finding by how much the water level is bent in each of these test wells. Right. So, and yes, this r is the radius or the distance of the test well. So there are two test wells that we're using. So this is Thiem's formula. So this is what we will be using over here. So let's just write down some of the information that we have. What is the radius of our well, the main well that we have? From the question, can somebody tell me what is the radius? Your diameter is 30 centimeters, so your radius is 15 centimeters. So going back, yes, very good. So your radius is 15 centimeters. So I'm just writing everything in meters because for the calculation we need everything in meters. So 0.15 meter. Now the test well. Let's talk about test well. So first one, what is the distance in which the test well is present? So this is test well number 1. The distance, let's go back to the question. So test well number 1 is located at 30 meters. So 30 meters away, and the drop down is 1.5 meters. So the distance is 30 meters and the draw down is 1.5 meters. Now for test well 2, the distance is 60 meters, right? Just to check, distance is 60 meters and the drawdown is 60 meters away and the drawdown is 0.6 meters. The drawdown is 0.6 meters. Right. Now let's try to find for the first test well. Let's take the case 1. For first test well, let's try to find the quantity of water that can be drawn out under these circumstances. So we're finding the quantity of water which is there discharged. So which is equal to km into, so let's keep, we don't know what km is because we do not know which aquifer it is. Nothing is given in the question regarding km, like nothing is given. So let's just keep it as such, km into our h. What is our capital H? Okay, this is the depth of the, oh yeah, I didn't write that. The depth of the well, we discussed this. So depth of the well is 40 meters. And yeah, so that is our capital H. We said that. So capital H would be 40 meters. So 40 square minus, so this is for the first one. So for the first one, the drawdown is 1.5, which means it will be 40 minus 1.5, the whole square, divided by log to the base 10 r. This is what we are going to find, r, radius of influence, divided by r, which is this one, r1, this is r1 and this is r2. So this is R1 because we're taking case 1. So that is 30 meters. So divide by 30. So yes. So this is our first one. So case 1. Now if we take the case 2 or the test 2, again Q. So this is, so one thing to note is that it's the same discharge that we're talking about. Because of a particular discharge from the actual well, this bend is happening. And whatever Q that we're calculating, the discharge is the same discharge. It's just that we're taking it from different test locations, but we're talking about one particular discharge, one pumping which has happened. So the same Q now in case of test Q will be, we'll again write Km because we do not know what Km is, H 40 square minus, here it will be 40 minus the drawdown here was 0.6. So we will take 40 minus 0.6 the whole square divided by log to the base 10 r divided by 60 because this is at a distance of r2 is 60 meters, right? So now as we said, q is the same. So q1 is equal to q2, or we wrote q in both the cases. So we can equate them both. So what becomes is that km into 40 square minus, so I'm not doing the calculation, we'll do it together, divided by log to the base 10 r by 60, sorry, r by 30, because this is the first one I'm writing, 1.5 is equal to km into 40 square minus 40 minus 0.6 the whole square divided by log to the base 10 r by 60. So if we equate it this way, our km and km will get cancelled, and now we can start solving this. So let's do this together, the solving part also. So we have 40 square. This one will reduce up to 40 minus 1 point. So 38.5 the whole square divided by log 10 into r by 30 is equal to 40 square minus, what does this work out to? 39.4 the whole square divided by log 10 r by 60. Everybody with me till here? No doubts, right? The calculation what we have written. So now we are interested to find r. So there's r in LHS and RHS. So we need to do some calculation over here. So first thing what we will do is we'll simplify these because these can be easily simplified and then written. So that is 1 So yeah, that just, can somebody, let me not write it. Can somebody do this simplification and tell me how much this 40 square minus 38.5 square work out to? And 40 square minus 39.4 square work out to? Everybody with me till here? Some confirmation?
Yes.
Okay, yes, very good. So let's continue the calculation. So I'm just making all the, like I'm doing some, I'm taking this here and yeah. So I'm just making all the R terms in one side. Okay, so this is a simple calculation. This can be easily simplified. So 117.75 divided by 47.64 works out to 2.471. 2.471, and we have two log terms over here. So if you have log, I'm just, I'll just write it in a different color. If you have log A by B, can we write it as log A minus log B? Can we write it this way?
Yes.
Yes. So now you can simplify this if that's the case. We can simplify it as log. I'm just omitting this base 10, assuming that we know that it's base 10. So it'll be log R minus log 30 divided by log R minus log 60. So this simplifies a lot, which is equal to R 2.471. Now let's cross multiply. So it'll be 2.471 into log R minus, yeah, so what is the value for log 30 or log 60? I'll just put it in bracket and then write in minus log 60 is equal to log R minus log 30. Yeah, so this is what we have. So how much is log 60? Do you have a log? Okay, so I think I'll just give you that. Like log 60 is 1.7781 and log 30 is 1.477. I think this should simplify the calculation. This is to the base 10 that we are talking about. Everything is to the base 10. I did not write it because we are doing it with respect to base 10. Now, can we simplify the calculation further? Sorry, I went to, yeah. My calculations can also be wrong, so please check. Is this what you're getting? Or if anybody has any doubts in how this is done, you can always ask. So what is R? Yes, I'm waiting for everybody with me till here. Or is there any doubts? Are you getting stuck somewhere? Vishaka, all good till here?
92 meters. Ni-
Nine,
95, 95, 95.
95 meters. Yeah, good. 95. So it comes up to 95.8 or 95.9 something. So we can approximate it as 95, 96 something. So that's good. You've got it right. So I'll just say, so we have it till here. So now in order to find R, we would take 10 raised to 1.982, which will give up to about 95.9, which we can approximate it as 96. So yes, I understood. Galif got it. Others, are you with me in this calculation? Is there any doubt how we got this, or because I know we're doing some log and we're doing some calculations, so the calculations are a bit tricky. So that's why. Vishaka, are you good? Yes, you mentioned you're good. Okay. Yeah. So then I guess Manoj, are you there? Everything is good, right?
Yes, yes.
Okay, thank you. And Piyush, sir, everything is fine, right? Till your calculations?
Yes, I am here, but I am trying to do those yes because it is very tough to read and
Okay, so
calculate
are
these
you
whole
getting
numbers.
okay, okay. Yeah, so that's good. It's good you said that. So, are you getting stuck somewhere or should we go a bit slow?
No, no, it's okay, but I am just trying to cope up with those mathematical this thing because I am a geographer planner.
Yes.
So I am
Okay.
almost, I think 10 years back I have done these whole things. Yeah.
Okay. Okay. Okay, I understand. Yeah, that's good. So yeah, I understand the mathematical part is a bit, especially the log calculations and raised to, which when we're not used to it, and we tend to forget it a lot. So I totally get it. So yeah, so
Yes,
that's
yes.
why we are going very slow over here. We will. That's why I'm going by every step by step. So if at all anything you're stuck, this is a very small crowd, so you can always put it in the chat box. It's wait for me, like I
Yes,
need
yes,
some
yes.
time, or you can speak out also. No issue.
Yes, ma'am, because I'm just trying to adapt that methodology first, then I will go to the mathematical part. That's why.
Okay, okay, okay. Yeah, very well. Fine.
Thank you, ma'am. Thank
Yeah,
you for asking.
yeah. So let's go to the next question, which is a continuation of this particular context which we started off with. The transmission coefficient of the aquifer Km is, that's a question. So yeah, so in the previous one, we did not know what Km is, so we just cancelled it out and we did. So now that we know what is R, we found R to be 96. Now that we know the radius of influence, we can easily find Km. It's a direct formula application uh, right now. So Q is equal to Km into h square minus h square divided by log to the base 10 R by R. This is the formula. So let's just see. Now, what is Q? Do we know Q? Let's go back to the question. As I said, Q is the same. Why? Because Q is the rate of pumping that is given in the question. The rate of pumping is 1500 liters per minute. So it's given in the question. So let's go back and plug it in here. So we have 1500. So the it's given in liters per minute, so we don't have to do any conversion over here. So equal to km. This is what we are interested to find. And h, what is h? The depth of the well, which is 40. So 40 square minus. Now this h, you can take any one. So we have two test wells, right? We had one at 1.5, sorry, one at 30 meter and one at 60 meters. So you can take any one. So let's take the one at 30 meters. So for 30 meters, the drawdown was 1.5. So we'll take the 140 minus 1.5 the whole square divided by log to the base 10. So our R will now be this R, which is 96, divided by, we have taken the 130 meters away. So we will write 30. Right. So just writing it here, 1500 is equal to this much. So let's do this calculation. This one we have already found out in the previous question, so you need not do it again. That was 38.5 the whole square, which was 117.75. Yes, even in fact, this whole portion, like even no, this you do not find. Yeah, so this calculation we'll have to do. So I'll just write everything in as take km to this side and write everything on one side. So sorry, this is this whole thing I just wrote it. Yeah, this is this whole thing. That's the calculation that we got. 117.5. So if I take everything to this side, it would be 36 divided by 96 divided by 30. 0.2. If you're finding it difficult, if you're finding it difficult to take the log values, I'll give you the log also. Log 3.2 to the base 10 is 0.505. Now the calculation should be easy. Oh, somebody has written km is equal to 6.433. Very good, Vashaka. Yeah, it is 6.433. That is the transmission coefficient. Very good. So let's see, is that, yeah, so 6.433. So this is the best option that we have. So option C is the answer. Very good. So let's proceed further. I'm assuming there was no doubt in that question. Let's go to the last question in this context. So what is the maximum rate of discharge of the well Qmax correct to 2 decimal places? So in the previous question, in the main question, it was given that the rate of pumping, which is Q, which was 15 liters per minute, or yeah, it was given in is it given in liters per minute, right? Yeah, it is 1500 liters per minute. Now, yeah, so this question we have been asked to find maximum discharge of the well correct up to 2 decimal places. What do we mean by maximum discharge? Which means you need to find Q. So the theory goes that you have a well and you're saying it initial water level was 40. Initial water level was at like the depth was the overall depth is at 40 meters. And now after drawing at a point, your water level is reducing to one particular point. That's what is said. Now this is because you've pumped some amount. You've pumped around 1500 liters per minute. This is what was pumped. Now the maximum discharge by Q maximum discharge, a Q max, what is meant is that all the water is taken out, which means everything is taken out, which means your H right now or the water level right now is equal to 0 in the well. So as we were discussing, H is the current water level which is there after pumping. So it reduces to a level such that there is no, like it reaches the bottommost point of the well. So H is equal to 0. So this is a very theoretical value. There will not be, we will not discharge the maximum all the time, but we just want to find out what will be the maximum or how much discharge can we take. So again, we will use the same formula. So the only thing is that H we will consider it to be 0. So Q is equal to Km into H square minus H square divided by log to the base 10 R by R. Right. So this Q is what you're trying to find. So it is Q max. Now Km we found in the previous question 6.4. I'm omitting the 6.433 for calculation. I'm just taking it as 6.4 into, now your H is the overall depth, the initial depth which was there, that is not changing, 40 square, minus your small h is 0 now, so 0 square log to the base 10, our r, which is the radius of influence, 96, divided by r, the small r. What will small r be? What will small r be? Anybody? That is one of the key to this question also. So in the previous questions, we were all calculating with respect to the test well. So let's just go back to the question. We were calculating everything with respect to the test well, and we were taking the depth of the, or the distance in which the test well is located. Here we are talking about the main well, that is when the maximum discharge, when, or when h is equal to 0, which means this value is equal to 0, the volume, the entire water which can be drawn out from that well, we are taking it out. So which means we are talking with respect to this well, and the radius of this well is given as 30 centimeters. Sorry, the diameter of the well is given as 30 centimeters, which means the test condition or whatever we are talking about is for this well, which means your R right now, the small r right now, will be 0.15 meters. Because we are not talking about the water, the entire volume of water being drawn out from the test well. We're talking with respect to the main well, so it will be 0.15. So let's go back to the question and plug it over here. So that will be 0.15, which is the radius of the well. So now this calculation is, it's not as difficult as the previous ones. So this value also I will give you if you don't find it difficult. So log to the base 10, 640 is about 2.808. Yes, so what does that work out to? Yes, I'm waiting for the answer.
Three six four nine.
3649. What is the unit? So we had our yeah. So by default, Q will always give us the answer. Like if you use this all these units correctly, we will get the answer in liters per minute. In the previous one also, we had 1500 liters per minute was the pumping. So given all the units that we're using, for instance, for radius, we're using meters, and that's the only, yeah, we are using meters. So given that unit, the answer that we are getting is in liters per minute. Now, if we go back to the question asks for meter cube per minute. So we need to convert liters per minute into meter cube per minute and then write. So your 3.3649 or 3649 would now convert to divided by 1000. So it becomes 3.649. So which is approximately 3.65. So is that there in any of the options? Yeah, so option C, 3.65 meter cube per minute. So we dealt with 3 questions. Yes, Parthasadi, correct. Yes, you put it right, rightly. Very good. So, any doubts in these three questions regarding the bending of water table and calculation with respect to test wells? No doubts. Okay. So let's proceed further. So, yes, this is a simple, so after doing such heavy calculations, this will be a very simple question. So we get a plastic tank with a volume of 1 meter cube and we fill it up with sand. We start adding water to the tank and the voids within the sand starts to fill up with water. We continue adding water until the water reaches the top of the tank without overflowing. In total, we added 330 liters of water. What is the porosity of that specific sand? So the information given, you have volume, plastic tank of volume, 1 meter cube, and then you're adding 330 liters of water. So again, the first thing is two units are different. This is in meter cube, this is in liters. So the relationship 1000 liters is equal to 1 meter cube. So we'll first have to convert this. We will convert the liters one. Let's keep the meter, let's take the unit as meter cube. If that's the case, the amount of water which is added is 330 divided by 1000. So that'll be about 0.33 meter cube. Now, what is porosity? The the ability of the material or the soil to hold water. So because of the more porous it is, more it will be able to hold. So or the amount of voids which are present inside a material to hold more water. So we have learned it in the lecture that porosity is equal to the volume of fluid which is added, or let's say or it's actually the volume of void which is equal to the volume of fluid because the fluid is going and filling the fluid. So let's write it properly. Yeah, so it's the volume of void divided by the total volume. So in this case, the volume of void or wherever the water is being filled is 0.33 divided by our total volume, which is 1 meter cube. So that is 0.33. Now the question is in percentage, so which means it will be 33%. Any doubts in this question? Okay, let's proceed further. Design an open well in fine sand to give a discharge of 3 liters per second when worked under a depression head of 2.5 meters. Assume the yield for sand to be 0.5 cubic meter per hour per meter square. So the question asks us to, yes, Galif, yes. You have a doubt?
This is regarding the previous question.
Yes.
So, is this the actual method which is used to find the porosity of any material
Oh, you're
and any
asking.
type of soil?
Oh no, that for that, the laboratory method, what is used, that's an interesting question. I don't know. This can be a method, but I'm sure there are maybe different methods are also there. I think I'll have to check that up. That's an interesting observation which you made on how do we find the porosity. So usually for most of the materials which we have, it's already tested and we know the porosity. So we take the theoretical values and we do the calculation. But yeah, what is a laboratory method of finding porosity? That's something which I also need to look up. I look that up and tell you
Okay.
next class.
Okay.
You can also look up, and if you find something interesting, you can share it with the class next class because this is an interesting observation.
Yeah, sure.
Yes. So we are in question 6 right now. So we've been asked to design an open well. So by designing, like it's not very complicated. The whole idea is we have to plan the radius of the well, or what is the diameter or radius of the well. So we have learned that in the theory we learned in order to, so we have different methods in order to find the yield from the well. So right now they have been given a specific yield for the sand. So all this, a lot of information is given. So basically when you're designing the well, we need to know how much of water we need to draw from that well. That's the only main requirement. Like, you know that I have this much requirement, I've got 1000 meter cube per second, like I need 1000 meter cube per second discharge, or I need that much of water from the well. So based on that, we will be designing. So there are different methods in order to find how much can be the yield from the well. So based on actual pumping, that is what I said. Like you need this much amount of water. So based on actual pumping, we can design the well. Or we have something called recuperation test, where we draw water from the well, or we take some water and then we see to what extent the water gets recuperated in order to find what is the yield of that well. So yield is again a property of the well. It depends upon uh, the aquifer type. It depends upon the porosity. It depends upon how much water it holds, how much water is available. So there are multiple factors which is there. So in our theory, we learned in order to find the yield from a well, Q, which is we can use this formula, which is the specific yield of the well. So it's written by C by A, which is the specific yield. This whole term stands for the specific yield into the area of the well. So this is what we are designing, the area of the well, into S, which is called the depression head. So what is depression head now? So we learned about potentiometric surfaces and hydraulic gradient. So for instance, if you have, if this is the aquifer, then if you have 2 points in the aquifer, the slope of this, or so water normally flows because of this depression head. Sorry, not depression head, because of the hydraulic gradient. So hydraulic gradient is nothing but the slope of two potentiometric surfaces. So the depression head is something which is derived from this hydraulic gradient. So what is the depression, or what is the gradient or the slope through in an aquifer? So these all factors contribute towards yield of the well. So again, I'm just giving very high level information about this, which by this you might not be able to understand everything. So I would urge you to again see the lecture. So the whole derivation on how we get this formula, Q is equal to specific yield in the area into depression head, is given in the lecture, so you can see that. So in this particular question, we have been asked to design a well, which means we need to find the radius or the diameter. And let's see what is given. So is Q given? Open well. So to give a discharge of 3 liters per second. So Q is given, and it's given in liters per second. But one thing is that in while finding, so specific yield is defined as the volume of water which can be released from an unconfined aquifer per hour, per unit area, per hour, per decline in water table. So for 1 unit decline in water table, how much of water can be drawn from the well? That is what is specific yield. So to keep in mind is that specific unit is always defined per hour. So here it's given in liters per second. So we'll convert it to the standard unit, which is meter cube per hour. In this case, it's meter cube per hour. So we have Q is equal to 3 liters per second, which we will convert it into meter cube per hour. So that would be first liters to meter cube and seconds to hours. So that we first let's do the liters to meter cube part. So that'll be 0.33 meter cube per second. Now into hours, so that'll be 0.0033 into 3600 because it's per second. So that works out to 10.8 meter cube per hour. Right? So this is Q. So we know Q. Now specific yield, that is also given, that is 0.5. So that is given to be 0.5. Now area we do not know, so I'm just leaving it as A itself. And depression head, that is also given 2.5 meters. So that's the depression which is there. So that is 2.5 meters. Do I have this page here? Yeah, okay, very good. So I'll just plug in all the formulas. So 10.8 is equal to 0.5 into A into 2.5. So I'm just leaving A as such. So A is equal to, let's do the calculation, 10.8 divided by 0.5 into 2.5. Yes. So how much does this work out to? 10.8 divided by 0.5 into 2.5. So now A is, I'm taking it as, so let's just look here. Design an open well. Okay, so so something which is missing in this question is that we need to find the diameter. By design, we need to find the diameter of the well. It's not the radius, you're talking about the diameter. So that's a small defect with this question. So I'm just correcting it here. So we need to find the diameter. So since we're finding the diameter, we know that area in terms of diameter is pi d square by 4. For a circle, it's pi d square by 4. So pi d square by 4 is equal to now 8.64. So if that is the case, d square is equal to 8.64 into 4 divided by pi. So d is equal to, yes, I'm waiting for the answer.
.3.
3.3. Yes, very good. 3.3. So is that there in the option? We have 3.4 in the option. So that's the nearest answer that we have. So it's option C, 3.4. Let's go to the next question. So these two will be the last two numericals that we will be doing. So it talks about the recuperation test. So it's very similar to the previous question which we did. So during a recuperation test, the water in an open well was depressed by pumping by 2.5 meters and it recuperated 1.8 meters in 80 minutes. Finds the yield from a well of 4-meter diameter under a depression head of 3 meters. So what this question talks about is that, so just to give a brief outline about the recuperation test is that, so you have a water level. Now you have certain water level. Now after pumping, the water level drops because of this pumping. So that is dropping by 2.5 meters. Now after some time, because as we discussed in the previous question, water from the surrounding regions can always come in. So water can keep coming in. And because of this, it recuperates or the water level comes to a certain height. So, sorry. Whatever was depressed from that, it came whatever, yeah, it comes up to about 1.8 meters. From 2.5 below, it comes up to 1.8 meters. And this happens in 80 minutes. This is what is given in the question. So this is a recuperation test in order to find what is the yield of the well or how much water can be drawn from the well. And this is the information which is given. In 80 minutes, whatever was depressed by 2.5 meters came up to 1.8 meters. So let's call this S1, the initial depression, and the second as S2, which is the whatever no, S2 would be the difference. Yeah, let's solve that. Yeah. So this is what it is. Now, you've been the question. Question 7 is asking us to find the yield from the well of diameter. So the diameter is given 4 meters under a depression head of 3 meters, which means the overall depression head S is 3 meters. Now, why this is? So I'll give you the formula. So we discussed Q is equal to C dash by A into area into S. This is what we discussed. So this S is this depression head that we are talking about, the overall depression head. Now, in order to find C dash by A, so in the previous question, the specific yield was already given. In this question, we need to find the specific yield. And to find the specific yield, which is the C dash by A, the formula is 2.3 by T log of S1 by S2. So this we are getting it from the recuperation test. So now T is the duration or the duration in which the recuperation is happening, and that is in hours, the duration in hours. And S1 is the initial drop down which is there, and S2 is the second, it's the drop down after a certain point. So your S2 will actually be 2.5 minus 1.8 because it's coming up by 1.8. So it's not 1.8, it's 2.5 minus 1.8. The first one, S1 is 2.5 because it's coming down 2.5. Now it's going up a bit more. So the S2 or the depression which is there at that particular point is 2.5 minus 1.8. Right. So if this is the case, let's find what Q is using this. So I'm writing everything together. We can solve it together. So Q is equal to the first one where we'll find C dash by A, which is in this particular case, what is C dash is, yeah, so C dash by A, sorry, C dash by A, that's what we are finding. It's called C dash by A is the specific yield, but the formula we saw, it's 2.3 divided by, so 2.3 divided by T. So what is T now? So T is 80 minutes is what is given in the question. Now 80 minutes, but we need to convert it to hours. So it'll be 80 by 60, which is 1.3 hours. So let's put that here. So it will be 2.3 divided by 1.33 into, now log of, that's the formula, log to the base 10 into S1 divided by S2. So S1 is 2.5, S2 is 2.5 minus 1.8. I'll just write 2.5 minus 1.8. Right. So this part gives us our C by A, which was there in the previous one, which was already given in the question, into the area. The area. So what is the area right now? We have given that the diameter is 4 meters. So which means we discussed before, area is equal to pi r square, which is equal to, in this case, the diameter is 4 meters, so radius is 2 meters. So that will be pi into 2 square, which is equal to 4 pi. So we have the area also. So let's plug this in here. So which is 4 pi into, now the depression head, the overall depression head, that is in the question, the overall under a depression head of 3 meters. So the overall depression head is 3 meters. So let's solve this. What does this work out to? Yeah, so let's solve it this way. Yes, 26.19. Okay. So what is 26.19? Anybody, any other answer? Just check your calculation once more.
36.
36, correct. Yeah, 36 is the right answer. So this works out to 36 meter cube per hour. So in the previous question, we saw that the unit of Q in this particular equation is meter cube per hour. Why? Because your specific yield is in hour and the standard unit we are taking everything in meters. Okay, so let's see whether it's there in the option. But option, everything is given in liters per second. It's not given in meter cube per hour. So we need to convert this into liters per second. So after converting this into liters per second, what's the answer? Or how do we convert this into liters per second? Or let's say, what's the answer after converting it into liters per second?
Is 10 in the option?
Yeah, yeah, correct, 10. So just to do, so it'll be 36 into 1000 divided by 3600. So this will go, so it'll be 10 liters per second. That's the answer. Right. So any doubts in these two questions, 6 and 7, which is about the recuperation test and to find uh, the dis the discharge or the yield of the well, not discharge, the yield of the well. Yes, correct. 10, 10, correct. No doubts. Okay, so let's proceed on. So we have a few theory questions before we wind today's session. So these might be a bit easy. Oh wait, we have one more questions. We only did oh sorry, we didn't do eighth question. My bad. We have one more question here, the eighth question before we move to the theory question. The diameter of the well to the yield of 8 liters per second under a depression head of 2 meters. So we've been asked to find the diameter of the well. So the previous in the sixth question we designed the well. So same thing, we found the diameter of the well. So now that we know the specific yield, we have already calculated the specific yield, and we have also calculated the overall discharge. We can find the yield of the well. We can find this is a direct formula application. So let's do that also and then proceed. So now in this case, it will be so we've been asked to find the diameter of the well. So Q is equal to C dash by A. I'm just repeating the formula into A into S. So in this case, so Q, sorry, yeah, Q if the yield is already given, so which is 8 liters. So it is, now again, the unit is 8 liters per second. So it is 8 into, we'll do the same thing, 3000, we have to convert it into meter cube per hour. So, okay, I think you all do the calculation. So it's in liters per second. So convert it. And then we have C dash by A, which is the specific yield, which we calculated in the previous question. So I'll just give you that value. That was, sorry, it's 0.955. We calculated in the previous question. So it's 0.955 into the area. So what is the area? That is what we are interested to find, A, and then S, which is given as 2. So what is A work out to? Or let's not, let's directly go to D square. You have a space here? Yeah, I have space here. Okay, you do the calculation and tell me the final answer.
A is 1.16 meters square.
A is 1.16 meters square. 1.16 meters square. Okay, can you check your calculation? Did you do the conversion properly? I see something is different. 5 by 4. Hmm. Just check that once more. I think something went wrong in your conversion from liters per second to meter cube per hour. Because one decimal point is, there's some difference in that. Just check that once. So I'm writing A as pi by 4 d square now itself because d is what we have to find. D is equal to 4.382. Very good. 4.38 is the correct answer. 4.37 to 4.38, anything you get, it's the right answer. Very good. So your A works out to actually 15 point something, 15.05, and your D works out to, D works out to 4.38 something. So it would be something like this. Your D would be 15.05 into 4 by pi. So this is your A into 4 by 5 pi, and your this, if you take the square root, you'll get 4.38, approximately 4.38. Galif, you figured what went wrong?
Yeah, the conversion. Yeah.
Okay, good. So everybody with me till here? Yes. So any doubts in questions 7 and 8? No doubts. Okay, good. So let's proceed further to some theory questions. So which among the following statements is or are correct? Greater the intensity of rainfall, higher the duration. High intensity storms usually have higher frequency. Frequency of rainfall cannot be predicted. Intensity of rainfall can be predicted. So let's go by option. The first one is greater the intensity of rainfall, higher the duration. Anybody, what do you feel? Is it greater the intensity of rainfall? Will the duration be higher or will it be lower?
False.
You think it's false?
False, ma'am.
Okay, why?
Ma'am, sometimes shorter duration also have heavy intensity. Sometimes longer duration will have less intensity.
Okay.
Depends upon the cloud, like how it is.
Yeah. So in general, the shorter the duration, the intensity will be high, is what is said. So the general principle is that we are, or to go by a very theoretical principle, if there is q amount of water which has to come down as rainfall, like the cloud holds q amount of water, and all that is coming down in one go. If the duration, if time t, the duration in which q amount comes down reduces, let's say for duration t1 the intensity is I1, and for duration t2 the intensity is I2. Now if t1 is lesser than t2, which means the duration is lesser, then the intensity should be high, because then I1 will be greater than I2. Why? Because it's the same amount of water which has to come down. So this is a very theoretical principle of looking at this. And as rightly said by Parthasarathi, when you, mostly what we observe is also like that. We always observe that there is, for short duration when it's raining, mostly there are heavy storms at that time. And when for long duration, for days or for weeks, if it's continuously raining for a week, then the intensity, it might have certain sprouts, like certain time there might be high intensity, but throughout it'll be like a low intensity which is there. So this option is false. Greater the intensity of rainfall, higher the duration is false. It will be lower the duration. Now the second one is high intensity storms usually have higher frequency. Is that right?
False.
False. Okay. Why? You say an answer, you need to explain why also.
Usually, the higher intensity storms, they are less frequent. They come once or twice a year.
Exactly, exactly. It's based on the observation. Like we know that high intensity storms are usually less frequent, and over the years we have found out methods also to find how frequently it happens. So, yes, so that comes to the next question. Frequency of rainfall cannot be predicted. Can it be predicted? The option says it cannot be predicted. Is it right or wrong?
False.
False, because frequency can be predicted. As I said, like we have found out methods by which we can predict frequency. So it says it cannot be predicted, so that's also false. Now, intensity of rainfall can be predicted. Is that right?
True.
Yeah, true. So, intensity of rainfall can be predicted. So, the answer which is right is option D, intensity of rainfall can be predicted. Okay, so let's proceed on to the next question. Dash is defined as a percentage of voids present in a given volume of soil or aggregate. This you need to answer because we have already discussed this in today's class. Is it the void ratio?
Porosity.
Porosity, yes, correct. We discussed this in today's class, so we don't have to discuss this further. It is essentially a void ratio, like amount of void which is present in the total volume, but it is termed as porosity. This is the correct answer, the correct term that we use. We don't use a term called void ratio. And water content and level of saturation, it doesn't pertain anywhere to this question, so we don't have to worry about it. Yes, so let's go to the next question. Yeah, so this is the just for an explanation. This is what we learned in our theory. Porosity is the total volume of voids in a soil divided by the total volume of soil. So this is the answer. Let's go to the next question. Among the following statements, the incorrect statement is infiltration is directly proportional to porosity of soil. At slow rate of rainfall, less quantity percolates to the ground and more goes into runoff. Ability of water-bearing stratum to store water depends on porosity and size of particles. Sand and gravel are the important aquifers for public water supplies. So we have to find the incorrect answer. So let's go option by option. Infiltration is directly proportional to porosity of soil. Is it right or wrong?
Right.
Right. Yes. So this again, we discussed when we were discussing porosity. So if the soil is more porous, which means it has more gaps in it, which means when there is water, when rainwater falls, more amount of water can infiltrate and percolate and get stored as groundwater. So the infiltration is directly proportional to the porosity of the soil, which means the statement is correct, which means it's not the answer because we have to find the incorrect option. Now, the next option is at slow rate of rainfall, less quantity percolates to the ground and more goes into runoff. Is this correct?
False.
False.
False. So you're saying at slow rate of rainfall, more quantity percolates into the ground, right? Yes. So that's why, because it gives when rainfall is continuously flowing, if it's heavy intensity rainfall, the percolation only some amount can percolate inside, so more will go as runoff if the duration of rainfall is less. So at slow rate of rainfall, more quantity percolates underneath because it can get more time in order to percolate. So more percolates into the ground and less goes as runoff. So this is wrong, which means it can be the correct answer over here. But let's see the other options also. The ability of water bearing stratum to store water depends upon porosity and size of particles. Is that right?
Yes.
Yes, we learned this in our lecture. So, in case when we are looking into aquifers, the ability of the water-bearing stratum to store water, it depends upon porosity, one thing, and also the size of porosity we discussed. Why? Because of this factor, and size of particles also, because more granular you can store more, or the based on the size of the particles, you will have more voids inside it because of the size of the particles, so you can store more. So the ability of water-bearing stratum depends upon porosity and size of particles. These are two important factors. So this is correct answer, which means this cannot be the answer here. Now the last option, sand and gravel are important aquifers for public water supplies. So this is also right. We have discussed this, which means this cannot be the answer. So the answer is B. At slow rate of rainfall, the correct statement is more quantity percolates into the ground and less goes into runoff. Very good. Let's go to the next question, question 12. The major problems plaguing groundwater management in India are over abstraction, depleted aquifers, pollution in the form of industrial pollutants, human wastes, and agricultural chemicals. Yes. So can somebody attempt this question?
All the three.
All the three. Yes, correct answer. Why? Because this we've already discussed in our first week. Also, we discussed that illegal abstraction or over abstraction can lead to depletion of groundwater resources. And in last class, we saw that there are certain rules in order to protect this. There are certain rules which the government has put, state-specific rules specific to each industry, each type that of usage the groundwater is put into, but we do not have any monitoring mechanisms for that, so that's also a problem. And over abstraction is a very common problem in India, so this is correct. Then aquifers are being depleted because of over abstraction. This is linked to this, so that's also right. And another issue is the pollution which is there. This also leads to the decline in quality of groundwater. So option D, A, B, and C is the answer for this. Now, question 13. The major chemicals found in groundwater include so the first option talks about calcium, magnesium, chloride, sulfide. Then B, we have iron, magnesium, sulfate, and lead. Then in C, we have lead, calcium, fluoride, arsenic, and D, arsenic, chloride, fluoride, nitrite. So this, I think somebody who has seen the lecture would be able to attempt this question.
D.
You saying D, arsenic, chloride, fluoride, nitrite. Okay, so yes, it's I agree. Arsenic is there, chloride, fluoride. But the question asks, what are the major chemicals found in groundwater? Anybody else? Any other option?
It may be C.
Lead, calcium, fluoride, arsenic. So I think you're headstrong on arsenic being present in water. What is the
Yes,
problem
yes.
if arsenic is there in water?
We-
Is it good?
It's a strong adverse chemical. That's what we know.
Yeah, it's not good. It causes problems. So if there's arsenic, there can be poisoning, and it is led to a lot of water-related problems also, leading to bad health effects, deformations, and all that. So we should not have arsenic. So it should not be a major chemical, right? We should have minimum amount of arsenic in our actual water. So the answer over here is that yes, arsenic is a part, but the nine major chemicals, arsenic is not a major constituent. These are toxic constituents which are present. But the major constituents are sodium, calcium, magnesium, potassium, chloride, sulfide, nitride, and silicon. So I think from here what we have is, so again, this one, fluoride should not be a major component. So we can rule out these two options. Then lead is not there anywhere. Like it's not a major component. So we can rule out this also. Lead is also not a major component. So the answer is calcium, magnesium, chloride, and sulfide. Let's see whether everything is there. Calcium, magnesium, chloride, and sulfate. Yes, all four are there. So the answer to this question is option A, calcium, magnesium, chloride, and sulfate. Okay, let's proceed on to the next question. So I understand the confusion which was there because we discussed about arsenic poisoning, but it, even in small amounts, arsenic is not good. So it's not a major component in our groundwater, but whatever is there, we need to remove that in order to make water free, in order to reduce the poisoning. So these are toxic in nature. To reduce the toxicity of water, we need to remove arsenic. Now, question 14. The flow of groundwater depends upon hydraulic gradient, characteristics of the aquifer, hydraulic gradient and characteristics of the aquifer, none of these. Can somebody attempt this question?
C.
C, hydraulic gradient and characteristics of the aquifer. Because yes, hydraulic gradient, what was hydraulic gradient? Again, just to go back, if you have an aquifer, if you have a aquifer and you have 2 points in the aquifer, so this is a potentiometric surface. Now this slope, so if this is HA and if this is HB, based on these heights, the slope of these heights, that's the hydraulic gradient. Now based on the hydraulic gradient, so water flows based in the groundwater flows based on the hydraulic gradient. So hydraulic gradient is important in the flow of water, and also the characteristics of the aquifer. What type of aquifer is it? We learned about Km, based the transmission coefficient of the aquifer. So the property of the aquifer, also whether it's a confined aquifer or it's an unconfined aquifer. So all these characteristics will also influence the flow of groundwater. So the answer is option C, hydraulic gradient and characteristics of groundwater. Sorry, characteristics of aquifer. Yes, so this is what we learned. Yeah, groundwater flows the hydraulic and also depends upon the characteristics of the aquifer. So this is what we learned in our lecture. Question 15. Dash states that the rate of flow, which is a laminar flow, is directly proportional to the hydraulic gradient and area of cross section of the soil. So which law are we talking about over here? Any guesses? Okay, let's go by, yeah, Darcy's law. Yes, Darcy's law. So let's go by the principle of elimination. Let's go from the last one. Newton's law of motion. What is Newton's law of motion? F is equal to ma, like force is equal to mass into acceleration. So I mean that's nowhere related to what we are discussing over here in urban utility. So this is not the answer. Then we have Archimedes' principle. What is Archimedes' principle? It's about buoyancy. The amount of water which is displaced is equal to the volume of, if you immerse a solid inside a fluid, the amount of fluid dispersed will be equal to the weight of the fluid, Archimedes principle. So that's also not one. The rate of flow cannot be based on Archimedes principle. Then we have Bernoulli's principle. So what is Bernoulli's principle states? Anybody? This, I think, briefly we have discussed in our lecture also, Bernoulli's principle. If you have not, we will discuss in the coming lecture. So, anybody? So, Bernoulli's principle says that when in a fluid, on a moving fluid, when there's an increase in speed of the fluid, then the pressure and there is an increase in, sorry, when the speed increases, the static pressure reduces, and at the same time, the potential energy also reduces. So this if no, yeah, maybe this lecture, this particular week 3, it was not there, but in the coming weeks, we will see a derivation of the Bernoulli's principle in order to find how water moves. We'll derive a formula based on that. So that's also not the answer. So we have Darcy's law. So we learned in Darcy's law, like again, going back to our hydraulic gradient, we learned that the rate of flow is directly proportional to the hydraulic gradient, which was again, we denoted by S, hydraulic gradient, and the area through which the area of cross section A. And then in order to change the proportionality sign, we introduced K, which is the constant that we are introducing. So KSA, this is Darcy's formula essentially. So the answer here, so wall flow Q is equal to KSA. This is Darcy's law. So the answer here is A, Darcy's law. Right. Now let's move on to question 16, which will be the last question. Dash is the difference between the levels of potentiometric surface at any 2 points divided by the horizontal distance between them. We have discussed this, so I think you can answer this very easily. Hydraulic gradient, potentiometric surface, both hydraulic gradient and potentiometric surface, none of them. What's the answer?
Hydraulic gradient.
Hydraulic gradient. So that's what we've been discussing. I think 2-3 times we already discussed what it is. So the difference between the levels of potentiometric surface divided by the horizontal distance. So going back, where did we discuss? Yeah. So we have HA minus HB divided by this distance. Let's call it L, this distance. This is what is the hydraulic gradient, or we denote it by S. That's the formula. Right. So Yeah, so that's all for that's all the questions that we have to discuss. So now we have our last 10 minutes. So if you have any doubts regarding week 3, whatever questions we discussed, or if you missed discussing any questions when you were solving the assignment, if you have any doubts, you can ask that. No doubts. Have you all started solving assignment 3?
No.
No, okay, that's
Yes.
fine. Okay,
Actually,
somebody,
difficulty level is a little bit high compared to other assignments.
yes,
These are questions, not
yes.
theoretical one.
Yes, I understand. That's why we did all the numericals here. Like we slowly went through all the numericals. So I think now it won't be very difficult because uh, I understand this assignment 3 has a lot of numericals. So once we sort that, then everything will be easy. And most of the numericals which are there in the assignment we have solved also, right, in class. So now it should be easy. Also, I assume that the solutions to assignment 1 and 2 are out. You've received the solutions, right, for assignment 1 and 2?
Yes.
Yes, okay. So in that also, if you face any difficulties, like if you have any doubts, you can ask that also. Okay, so if there's no doubt, we can wind up for today. We have 5 more minutes. So we can end the session. I will be there for 5 more minutes. I will log out only at 9. So till then, if anybody has any doubts, you can stay back and ask. Or if you don't have any doubts, we can end. Thank you all for joining and thank you for being an interactive audience. I think a lot of you have put in the chat box and Galif, I think Galif just logged out right now. Galif was always saying the answers also. So thank you, Parthasarthi, thank you, Piyush, thank you, Vishaka, thank you, Manoj, thank you all.
Uh,
Okay. Thank you, madam.
Thank you, ma'am. Just one query.
Yes.
Uh, that what we call out the groundwater fundamentals. What is the major difference between rural area and urban area groundwater table? Like, if you have anything
Groundwater
on that.
table, what's the difference? Okay,
Ah,
the rate of the level of groundwater will be different for both rural and urban area, and it's not only different for rural and urban area. Within the rural area also, it'll be different. Is that what you're asking?
yes, yes, yes. Major, what kind of what I tell you, what I telling that what kind of major characteristics for that for those groundwater tables for that urban area or for that rural area, like main characteristic if you
Okay,
know
so
it.
in our groundwater fundamentals, if you look, what we learned was that the different factors, like for instance, we started off with infiltration. What causes
Yeah.
infiltration? So again, I'll just yeah, that's an interesting question that you have asked. So we can work that out together because it's something. So let's say you have an urban area and you have the rural area. So let's go by each principle. So you have infiltration. So infiltration rate
Yes.
again depends upon the material, the surface where it is.
So,
So we know that in urban area there's a lot of build up spaces and infiltration can be hindered because of the material which is used. So we can say infiltration to an extent will be lesser. I'm just comparing it. So infiltration will be a bit lesser in urban areas than in rural areas. We can claim that because of the build forms and all that. Then, so this is
yes.
the amount of water which is seeping in. Then we also learned about percolation rate. So percolation
Hmm.
is the movement of water inside the soil, which is, so you have, sorry, you have the soil. So infiltration is it going underground. Now in the soil, inside the soil, the groundwater, underground soil, how it percolates. So now this we cannot differentiate based on rural or urban alone. It depends upon the soil property. So within an urban region itself, what type of soil it is underground, what type of region it's located. So urban again mainly. So this comes your land use or the actual land, the soil properties. Urban just means that this is being used for a particular, or it's an urban, it's more developed, it's more of an urban setting. So let's talk about percolation. So in percolation it depends upon the soil property. So that within an urban area itself, it can have different soil properties. Within a rural area itself, it can have different soil properties. So percolation rate will also be different for different regions. So while we are assuming, while we are doing this comparison for urban and rural, there are other small divisions also which we can do. Then we have
Okay.
the groundwater or the water bearing stratum or the aquifer. So that aquifer will also vary. The aquifer properties will also vary. So these are the soil properties. Now again, we have the yield of the well. So how much pumping, how much will be taken off from the well? That is also there. That also depends upon the groundwater table properties, right? So the yield of the
Yes.
well,
Yes.
again, in urban areas, there would be more pumping because there are more, by urban, by definition, let's say that there are more industries in that area. There's more population in
Yes.
that area. So you will be pumping more, which means the water table will bend more in urban area than in rural area because you don't have that much of requirement in the rural area. But one more factor would be in rural area, the frequency of wells might also be less. Like for instance, it might be separated around for let's say once in every 2 kilometers you have a well. But in urban area,
Yes.
you don't know that frequency can vary. Like you have an industry coming up or you have a housing complex. Sometimes
Mm.
within a housing complex, within our own house boundary, we might want to dig a well. So maybe for every 20 to 50 meters, we might have a well compared. So
Yes.
again, this is influencing the groundwater yield or the amount of pumping that we're doing of groundwater that we're taking through these wells. So yeah, so there are many factors. So based on all, so in our lecture we learned about these characteristics, and based on these characteristics we can actually tabulate and draw a comparison chart. So that's a very interesting exercise that can be
Mm.
done.
I can try.
Yes.
Thank you, mom. Thank you.
Yes.
Thank you,
Anybody?
mom.
Yeah, thank you. Thank you for asking that question. Okay, so if we have no other doubts, then we can call it a day. It's already 9. So thank you all once again for joining, and see you next week with week 4 for week four's discussion. Have a good night.
Thank
Ma'am,
you.
Yes, you have a doubt?
no, ma'am, like this session is recorded or something. No,
Yes, it's recorded. It's available in. So are you not being given the link of the recorded sessions? A mail
no,
is.
ma'am.
Oh, it's is it
That's
not?
why I'm
Oh,
asking.
okay, fine. Um,
So actually, no, no, actually it is there, madam. He must not have been seeing it. So
okay.
in the standard format, it's there. In the last bottom.
Sorry. So could you just enlighten where is the link available of the recording?
Uh, in our normal link, when all assignment are there,
Mm-hmm.
just at the bottom, last
Okay.
bottom is the recorded video links. But first and second one are there. This third
Mm-hmm.
one will be available after 2 3 days.
Yeah, so it'll be
Most probably.
available soon. So now I'll upload
Yes.
it. So it's basically on YouTube. So I'm giving the link, YouTube link, which will be shared to you all. So
The
it should not.
first two are available
Yeah.
because
So
last one I was not able to attend, so I have just listened the recorded one.
okay, great, great. Yeah. So the links are available. Oh, that's good then. Yeah. So this within another 2 days,
Okay,
the
ma'am.
link
Then
will be
I'll
available.
follow it.
Yeah.
It's
Yeah.
available.
Okay.
Madam, one small request:
Yes.
if there are lecture materials also,
Huh.
because for first and second week there were lecture materials. For third one and fourth one, lecture materials are not there. If lecture materials are available, it will be nice one to
Oh, so by
study.
lecture material, you are talking about the presentation, PowerPoint
Yes, yes, yes,
presentations in the PDF.
yes,
So
yes.
that's available, right? For third and fourth, is it not available in
No,
NPTEL?
yes, no, it's not available. For first and second one, they are available.
Oh, okay. Then I'll have to check to that. So usually it's made available. So as and when the lectures are there, you can download a PDF also along
Yes,
with
yes.
it.
I have seen it. First, second week are there. Third one I am missing. Third and fourth are missing.
Oh, right. Okay. Thanks for letting me know that. I'll contact NPTEL team.
And recorded these live sessions are definitely there.
Okay, great. Yeah. So yeah, so this one it's very good you pointed that out because that might
Yes,
they might have forgotten
yes,
to put it, but it's important to put that because
yes,
otherwise how will you solve the assignment? It's very important.
yes, yes,
Okay, fine.
yes. Thank you. Thank you.
Okay, so We shall end then. Thank you all. Bye bye. See you next week.
Thank you, ma'am.